So first of all, we talked about doped silicon or doped silicon conductor in general. Okay, we see two types of these doped silicon materials. We see the N-type material in which, in which we dope or we add impurity to the atoms of silicon, such as phosphorus, that has 5 electrons in their valence band. And for B-type, we do the opposite. We put, I'm sorry, not the opposite, similar thing, but atoms with 3 electrons in their valence band. Okay, so this will create a hole, ideally with each one, with each boron atom added, and this will create an electron. This will create an electron for each phosphorus atom added. Okay. We also mentioned that Ni, the intrinsic doping or the intrinsic carrier density of the semiconductor is always constant. Okay. It does only depend on temperature and the energy gap, which is, we can say, the material, because each material has its own energy gap. Okay, we can control the temperature, but we can't control the energy gap in the same material. And Ni squared is always equal to N multiplied by B, the electron carrier density multiplied by the whole carrier density. And this is always equal to constant. For N-type, N will increase, B will decrease, so that the multiplication will still hold in I square. And for B-type, we have something similar, but the opposite way. So B will increase, N will decrease, so that again, the multiplication will be constant. We also talked about the effect of temperature on extrinsic silicon, and we said that we have now 2 silicons. We have the intrinsic silicon, in which there is no, impurity atoms added. So that we call the carrier density Ni in intrinsic. And we have extrinsic semiconductor or silicon now, in which we added, some impurities like phosphorus or boron. And we see that by increasing the temperature, N doesn't increase so much, but B increases. And some increases, I mean, with a considerable amount. And at some temperature, maybe they will be equal. And the extrinsic silicon will turn it to be intrinsic silicon again. This is for N-type. This is for N-type. And for B-type, we have a similar thing. B will stay the same with the temperature increase. It will not increase so much, but N will increase will increase with a huge amount, we can say, relative to its original value. And again, at some point, the intrinsic silicon will become, the extrinsic silicon will become intrinsic silicon. Okay, so this is a recap for the last lecture. Let's now, yes, we also talked about the types of currents in semiconductor, and we mentioned the first type of currents, which is the drift current. And we said that in the beginning, if you have in the ideal situation in free space, there is no material or something, if you have just an electron in free space, okay, it will move under electric field based on these equations. But in material, it's different. If the electron is inside a material, the story is different. We have impurity atoms, we have thermal vibrations. So the movement of electron will not be straightforward from the negative to the positive. Yes, from the negative to the positive, because the negative terminal of the battery pushes the electron away from it, and the positive terminal of the battery attracts the electron towards it. But this motion will not be, straight line. You might have collisions with atoms. You might have also deviation, something like this. So if the electron, which is negative charge, approaches close by to a positive ion, and we said that when the phosphorus atom loses electron, it becomes a positive ion, there might be some attraction force. So it will deviate in a way like this. It will not continue in its original path or course. And we said that the drift velocity, or the velocity of the electron in that case, is proportional to the electric field applied, and the constant of this proportionality called mobility. And since we have two carriers, we have two mobilities. We have mu n and we have mu p. And the last thing, yeah, so Vn is equal to minus mu n multiplied by the electric field. And again, here is the minus because the electrons moves against the electric field. Yes, there is a force, but this force is in opposite way of the electric field. And Vb, the drift velocity of the holes, is equal to mu b multiplied by the electric field, epsilon, okay? And lastly, we said that mu is just a constant for the material and also for the carrier type itself. So for silicon, for example, we have at room temperature, mu n is 1,350 and mu b is 480. And we said that always the mobility or the motion in general of holes is more restricted than the motion of the electrons. That's why you have always mu n larger than mu b. Okay, good. So we'll have example on this. This example isn't just in the book, but it's a good example. So let's here have an example. If you have some sample of any type material, and here is the positive terminal of a battery, and here is the negative terminal of a battery. And assume that this voltage is 1 volt. Okay. And the length of this sample is 1 micrometer. Yes, find Vm. Okay. This is number A. And number B, time required for electrons to travel from, let's call that A and B, from A to B. Let's call this terminal here, the start is A, is called this guy B. And remember, the current that will flow in this sample is going in that way. And always the convention we have is that the current direction is opposite to the electron's directions, but the electron will go in that way. So this is the net direction of electrons. Of course, they move, in the, in some, random manner, but they have an overall direction or net resultant direction from negative to positive. Okay. We know that, so this is a solution now. We know that Vn. Let's talk about here the absolute values. Okay, just forget about the sign. We just need the value itself. So Vn is equal to mu n multiplied by epsilon. Okay, يعني this is a silicon material, so this is silicon. Okay, so for silicon the mu n is 1350 epsilon. So we need to know epsilon to calculate Vn, the drift velocity. Okay, but we know that epsilon is just the electric field is always in, not always, but in most of the cases we can say is equal to the voltage divided by the distance. Sometimes the relation is not linear. This is a linear relation between the electric field and the voltage. Okay, so that it's just the voltage divided by the distance between the two terminals of the battery. Okay, so we assume here that the electric field is linear inside this sample. What is the voltage? It is 1 volt, very easy. What is the distance? Is 1 micrometer. So we have a million volt per meter. Okay, because this is 1 micrometer. So I just multiplied by 10 to the power minus 6 to convert it to meter. You can, since this guy, if you remember guys from last time, this is measured in what is, yes, centimeter square per voltage second. Since we usually use centimeter in this course, so it's better to convert this to centimeter. So it will be, this will be multiplied by 10 to the power 2. So this is 10 to the power 4 volt centimeter. Okay, good. So we know epsilon. Now we can go back to Vn and calculate Vn. So Vn is equal to 1350 multiplied by 10 to the power 4. So this will give us, you know, yeah, 13, 5, 3 zeros. Oh, we made it again with meters, but anyways, that's fine. That's fine. Meter per second. Okay. Anyways, this is just a matter of dimensions. Okay, meter, centimeter, but it's preferable always to have centimeter dimensions. Okay, good. Okay, what is, so this is A. Now let's go to B. He said that what is the time required for an electron to travel from A to B? This is very easy. Okay. So we know that velocity is equal to distance by time. Distance. Let's write it just to not confuse the symbols. Okay. So the velocity, we have it here in meters. We have the distance, it's 1 micrometer, and just we want the time. Okay, so we can easily calculate the time. It will be 7.4 picoseconds. And pico is just 1 to the minus 12. Okay? It's not hard at all. Okay? And the silicon in that case, whether it's N type or B type, is just like a resistor. Okay? Since we are talking about drift currents, and drift currents is the currents that we all the time dealing with in circuit theory. The one in your mind right now, I mean, is the only thing that you studied so far, is the current that goes through resistors. Okay, And in that case, this sample is just a resistor for us. So in order to continue our analysis here, we need to know what is the resistivity or the conductivity. You know the resistivity rho, okay? Each material has a constant called resistivity. How much resistive is this material to the current? And we also need to know or of course the conductivity, and which is just the reciprocal of this resistivity, 1 over rho. So sigma, the conductivity, is always equal to the 1 over rho. Okay? So we need to determine the conductivity or the resistivity when we dope silicon, semiconductor in general. Okay? So let's do that. I called it drift current derivation, this slide, because basically to know resistivity, we need first to calculate the current, as we will see. So we will assume here that we have okay, a sample of silicon like this. It has width of W. It has thickness of H. So this is H, this is W. And let's assume a piece inside this sample that has a length. So let's, yes. So this piece in here has a length of V, and this is any type, by the way. I am assuming here it's any type. So this is Vn. So Vn, yes, Vn is just the velocity, okay? No worries. Something per second, 1 meter per second, something like this, 2 meters per second, okay? So I will just take this number, which is 2 meters per second, 3 meters per second, whatever, and choose just a piece in this big sample, okay, with a length equal to this value, which is 2 or 3, whatever, equal to Vn. So this is Vn meters. Okay, good. If you have a distance equal to Vn, then you are sure that whatever travels from this point to this point will travel in 1 second. So if the electron at this point, if we measure the time of the electron, it was passing this point and it was t, for example. So when we measure the time at this point, it will be t plus 1 second. Okay, good. And what is the definition of current? Current is the charge that passes through time. I mean, divided by time. Total charge that passes through a certain amount of time. If we know that 5 coulombs passes through a material, some cross section, or even some volume, in, for example, 1 second, then the current is 5 divided by 1, it's 5 amperes. That's good. So we know that if we calculate the charge inside this small volume that has length of V, width of W, thickness of H, then we can know the current, because this is a volume, or this is a total amount of charge that passes through 1 second, because this is 1 second, remember. So whenever we pass from this location to this location, we pass in 1 second. Good. So we need to know the charge in that volume. So what are our carrier density? What are the carriers here? The carriers here is electrons, mostly electrons, okay? Because this is any type. We usually neglect the holes current when we talk about N-type materials. As you see, for example, from last lecture, N was 10 to the power 16, at the same time, B was 10 to the power 4. The difference is 1 trillion. Good. So the carrier density is N. But remember, this is carrier, electron carrier per centimeter cubed. So this is density. You know the density in this location in here. It's N. If you multiply this density by Q, and here is minus Q because these are electrons. So you know that the total charge density in Z. So remember, N is just a density, it's not a charge. So to convert it to a charge, you must multiply by the charge in coulombs, which is Q, a charge of 1 electron. And here is electrons, so I put the minus. Okay, this is now a charge density. This can be called a charge density per centimeter cube. If we multiply it by the volume, this volume, we get the charge. We get the total charge, which is the current in that case, because we know that this will pass in 1 second, so this is the current. So we multiply this by the volume. What is the volume? It is the width here, W, the thickness, H, and this length, Vm. And this is the current, In. What is this? This is the volume. Good. And you know, I'm sorry, yes, and you know Vn is equal to minus mu n epsilon. So we'll just take out Vn and put its value here. So In is equal, minus will go with minus, so Qn W H mu n epsilon. Good. So this is, by the way, this is very specific to this example because we assume the geometry is with this shape, but the geometry may be cylindrical, for example. You don't know the geometry, so you want something, you know, that doesn't depend on the geometry. So let's normalize this by using the current density, J. So we know that the current density is always equal to the current itself divided by the cross-section area. And in that case, the cross-section area is this one here, which is W multiplied by H, and our current is In. So this is equal to Qn W H mu n epsilon over WH. So Jn, because this is electrons carriers, equal to Qn mu n epsilon. That's very nice. From physics, we know, if you guys studied, you know, electric field theory, you know that Jn, or J in general, equal to sigma epsilon. The current density is equal to the conductivity of the material multiplied by the electric field. So this is, in that case, sigma. And in specific, it's sigma n. So Jn is equal to sigma n epsilon. So we can know that the resistivity now, rho n, which is 1 over sigma n. It's 1 over q n mu n. Can we do the same for B-type? Yes, of course, we can do the same for B-type as well. And we will get almost similar equations. So for holes, JB is equal to QB instead of N. Mu B is the mobility of holes multiplied by epsilon. So sigma B is equal to QB mu P, and rho B is equal to 1 over QB mu B. And the total current J total, is equal to Gn plus Gb. It's equal to Q mu B plus mu N sigma. And remember, they are not canceling each other. So the holes, as a charge, moves in the opposite direction of electrons, okay? But the conventional current is always opposite to the flow or the direction of movement of the electrons and in the direction of holes. So both are the same direction. So they are not canceling each other. And remember, the baseline that the holes, there is no holes, you know, there is electrons that moves from a gap to a gap just to fill these gaps or holes, okay? It's just a convention that we are using, the concept of hole. Okay, so this concludes, okay, the drift current, you know, analysis. Let's take an example from the book. I don't know. Yeah. Let's take an example. So the example says, okay, what should be the doping densities? It's plural, not singular. Okay, in order to achieve equal holes and the electrons, and the electron currents. So from this example here, In is equal to Qn W H mu n epsilon, IB equal to QB W H mu B epsilon. Or you can just generalize it and write it as Gn and Gb. It's fine. Okay. So we want In to be equal to IB. So Qn WH mu n epsilon equal to QB WH mu B epsilon. WH goes with WH, Q goes with Q, epsilon goes with epsilon. So N mu N equal to P mu P. Now let's go back to the question. What is the required doping densities? So here the sample is a little bit different. We're gonna dope the silicon with both, with phosphorus and boron. Okay? To have a mix of N-type and B-type material. And at that case, it's not exactly N-type, it's not exactly B-type. So now we wanna, this what will control our density, because we wanna equal currents. So we wanna be sure that n mu n equal to p mu p. Mu n is constant, mu b is constant. Okay, so n should be, for example, p mu b over mu n. Yes, it's A4. So let's continue in another slides. Okay. So n mu n should be equal to b mu p. So from that, let's set the page size as A4 as usual. Okay. So based on that, n will be equal to p mu b over mu n. But now, how much doping I should do? How much Nd, how much Na? How much phosphorus atoms, which is Nd, and how much, yes, phosphorus, and how much boron atoms, which is Na. I want to add donor atoms and acceptor atoms such that, with some amounts, such that N equal to B mu B over mu N. Okay? Okay. So let's go back here to the neutrality of the material. Fact. We said that whenever you put atoms, impurity atoms, and you create N type, either N type or B type, the material charge will be neutral. The number of electrons will be the number of positive charge will be equal to the number of negative charge. In that case, our material has both Na and Nd. So it has both N and B. So the negative charge density should be positive, equal to the positive charge density. Just density. Okay. So what are the negative charge we have here? We have N, and remember we have the acceptor atoms. The boron atoms, when they have electrons, they become negative ions. And what is the positive charge? We have B, the holes, and we have the donors. Because the phosphorus atoms, when they lose electrons, they become positive ions. Okay. Remember, those are the unknowns, and we have a relation between N and B. So let's put here this relation B mu P over mu N plus Na equal to B plus Nd. Good. Yes. So this is an unknown. This is also unknown, and B also is unknown. So we need another equation here, which is, we know that Np equal to Ni squared. Okay. So from this equation actually, and also this equation in here, since mu B is known and mu N is known, and the Ni, this is a silicon, is also known. So you can say that B equal to 1.68 Ni. or 1.68 multiplied 10 to the power 10. So from these two equations, I just forget this step. From these two equations, this one, let's call it 1. And from 2 here, from 1 and 2, we get B equal to this amount. So B is now known in this equation. Okay? So what we're gonna do is actually we still have two unknowns, right? But what we're gonna do is we're gonna choose one of them. We're gonna choose either NA or ND and calculate the other one based on the value we choose from the first one. So for example, if we choose ND equal to 10 to the power 10, okay, whatever, okay, and go back here and calculate NA, NA will be equal to 284 multiplied by 10 to the power 10. So if you have a silicon, intrinsic silicon material sample, and you dope it with 10 to the power 10 donor atoms or phosphorus atoms and 2.084 10 to the power 10 boron atoms or acceptor atoms, then if you measure the current that came from IN and the current that came from only IB, then you will find them both equal. Okay. So this concludes the first type of currents, which is the drift current. Okay. So let's go now to the second type of currents, which is the diffusion current. Diffusion. And here is an example from an ink in water. When you put just one drop of ink into a cup of water, it diffuses everywhere. Not just down due to gravity, no. It goes left and right everywhere. Just like this. And we have a similar phenomena here in our semiconductor as well. So if you have a piece of silicon, okay, and you inject, for example, electrons somewhere, somehow, okay. If you inject, of course, acceptor atoms from some point, but not the other point, okay. So that the density of, if this is x-axis, the density of the electrons will become, for example, like this. It means that the electron density N here is larger than here. It's different. It's not uniform all over the sample. Like, so before we always assume that the electron density N or B, the whole density, is uniform all over the sample, the silicon sample. But here it's not. Here we intentionally create a profile, a non-linear profile. I'm sorry, not non-linear, not uniform profile. Okay. So that the density of carriers at some point is different from another point. And maybe this profile takes this relation, for example. Can be any relation, can be linear, whatever, with X. So N here is actually a function of X, or whole, or the wholes, when we talk about the wholes. B is also a function of X. So what's gonna happen in here is that since there is an excessive charge here, so there will be a diffusion in that way. a diffusion from the highly doped parts to the low doped parts. Diffusion from highly doped parts to the low doped parts of the semiconductor. And when you have a charge moving, then you have a current. Okay? So we can also create a current just by, varying the doping density everywhere in the sample. If it's not uniform, you will have a diffusion current. Good. So this current now, I diffusion, is actually proportional to, yes. If you have more and more variation, gradient, then you will have more current. So I diffusion is proportional to dN by dx. What is dN by dx denoted for? This is the slope, we can say, okay? How much variation, the derivative of n with regard to x. If you have large variation, then you will have larger current. Because if you have a large variation, that means between two locations, there is a large difference in the doping density n, or the carrier density n. And also, if we talk in a geometric way, if you have larger area, you will have also larger current. So I also proportional to the area. So based on these two proportionalities, I will be equal to A dN by dx. And we need also to put the charge Q. And we need a proportionality constant, which in this case we call it dN, diffusion constant. Something like the mobility, mu n and mu b. Sometimes you call it diffusivity. Diffusivity of the material. So it's something relates to the material. Each material has its own dN. And this is, in this case, it's IN. Do we have the same for the holes? Yes, we have the same. So again, yes, and just to normalize stuff, and we always don't want to relate to the structure or the geometry of the material. So we like to express it as Jn, current density, which is just In over A, the area. So it's Q dN by dx. For holes, we have the same. If you have again material like this, semiconductor, and you inject acceptor atoms from here, borons, for example, so that you have something like this, a variation, whatever the variation relation to x, it might be linear, it might be something non-linear like this. This is B. You also have IB, and I will put here a negative sign, and you guys have 1 minute from now to think about it. Why we have a negative sign here? So the answer lies in dB by dx and dN by dx. Okay. So if we look at the change, okay, of B with X here, let's assume it's a linear relation, something like this, just linear. Okay, what is dB by dx? It is a slope, right? The slope of this line. So basically what will happen is that since we have high doping here than here, then the holes will move in that direction. And the direction of holes is actually the direction of its current. So IB is also in that direction. But dB by dx itself is negative because it's a negative slope. Okay, so we need to put this negative sign here so that we cancel out the negative signs that will come up from the derivation of B by dx. So let's do the same for our electrons. So here there are more electrons than here. So the electrons will move in that direction. And the current is opposite, right? But we know that dN by dx will be negative if we, for example, assume again linear relation like this, the slope will be negative. So this will give us a negative. So we don't need to worry about the direction of the current. Okay, it will be based on dN by dx, which is negative. It will be in opposite direction of the movement of the electrons. That's why we put these signs. Okay, that's good. That's very good. So let's see if we have example here. Yes, and for any material in general, okay. Let's go back to our lovely color. J is equal for any material. If you have any silicon in general and it may be doped by boron and phosphorus at the same time, so J total, like just as what we have done with the drift current, is equal to Jn plus Jb. So it will be equal to Q dN by dx minus dB by dx. Okay. And again, don't worry about the sign here. Okay, because the dB by dx will equalize it. Okay. Good. So in the book, let's talk about the example. One of the examples, the example. Now I have the example number, Muhammad. You were asking about the example number. For this one, I have the example number. So exercise 2.9 says that if you have a profile, if you have a material, okay, and it's any type material, and you have n as a function of x, is basically something like this. So if this is the x-axis, so you have a material, the material has some length L. At x equal to 0, we have we have the density of electrons equal to n capital, and at L it's equal to 0, and it's linear as you see here. Okay, so yes, it says that find Jn. That's it. That's the question. Okay, and sketch it. So let's do that. Okay, Gn should be equal to Qn. I'm sorry, Qdn, dn by dx. Okay, so in order to get this derivation here is a derivative here. We need the relation that relates n to x, right? So this is a linear relation, as you see here. Here from 0 to L. You just want the answer from here to here, not beyond or before. Okay, in that region from 0 to L, n is actually equal to the slope multiplied by x plus some constant. Let's start by the constant. What is the constant here? Is that this is the intersection of this line with the vertical axis at 0, which is n. And what is the slope? The slope, just take 2 points, for example, these 2 points, okay? And so this, the value of n here minus the value of n here over the value of x here minus the value of x here. So the value of n here is 0. The value of n here is n. The value of x here is L. The value of x here is 0. So this will be give us minus n over L x plus n. Let's have a check. If you put x equal to 0, n should be equal to n. If you put x equal to 0, this will be cancelled, so n will be equal to n capital. And we should another check. If you put x equal to L, n. So if equal to L here, this will be cancelled with this. So minus n plus n will be 0. So we are right. Good. So Jn is equal to Q dn. And now what is dn by dx? This guy. Minus n over. And let's have here a moment. This is a constant, right? So n here, he assumes it's a constant in this example. Is a constant. dn is a constant for the material. I will give you in a moment the value for silicon, for example. And q is a constant. So we can sketch based on that also the relation between j of x, gn of x, and x. First, it's a negative value and it's a constant. For example, here, it's just a sketch. From 0 to n. And what is this value? It's minus q dn n over n. This is just a sketch. It's a constant, okay? And just one final observation. What's meant by if we say that the current is constant? That means that the electrons that we inject at x equal to 0, all of them will be ejected at x equal to or reach x equal to L, okay? But this is not usually the case. Usually when you inject something from one side, not all of them go or make it to the other side at x equal to L. Some of them will be recombined by holes in the structure. So don't expect constant like this. Okay, good. So just one final note here about dn. So dn for silicon is equal to 34 centimeter square per second, and watch out for the dimensions all the time. And dB as usual less than dn equal to 12 centimeter square per second. Just like mu n and mu b. Again, here dB is less than dn. Again, the diffusion of electrons is faster than the diffusion of the currents, of the holes. Okay, that's good. There is another example in the book, example 210. Please read. Of course, you by default you should read the part of the chapter that I explain in any lecture, okay? But just take a look at example 210. It's very useful. It's based on this example as usual. Okay. So one last thing, it's Einstein relation. So we talked about two different phenomena, the drift current and the diffusion current. And we see that the physics is different. This is completely different than this. This is a completely different phenomena than this. Although Einstein could relate them to each other. And he discovered this very interesting relation that dB or D over mu equal to constant, which is KT over Q. This is very useful relation. It's called the Einstein relation that relates two completely different phenomena to each other. D over mu, D is from the diffusion current, and this is from the drift current, is equal, if you divide both together for any semiconductor, and that's really interesting, it's equal to K Boltzmann constant temperature in Kelvin over Q. Okay, and why this is constant, of course, at equal temperature. Okay, and this is at T equal to 300 degree Kelvin. It's equal to electron volt. Remember, if you remember maybe from our second lecture or first lecture, I can't remember exactly, we said that K multiplied by T is actually energy. And since it's a temperature, it's a thermal energy. So for any temperature, if you want to know how much energy this temperature will exert on a material, just multiplied by the temperature in Kelvin by K, the Boltzmann constant. If you divide by Q, you are converting from joules to electron volt. That's it. Okay. And sometimes they call that thermal voltage. That relates to this electron volt stuff, because we said that electron volt means the energy required to move electron between a potential of 1 volt to 2 electrodes, and this electrodes has a potential of 1 volt. Okay. So based on that, I published a homework, which is due next Tuesday. Okay, 10 a.m. as usual. Okay. Okay, that's good. So what else we have here? Okay, that's enough for today. Okay. So next time we'll start by the B injunction, which is, the first really interesting application of all such physics that we studied so far. Okay. And then we gradually will delve into circuits or applications. So the course will back to be analog circuits.